In the previous lecture, we started the discussion on different kinds of codes for digital systems. In that particular discussion, we looked at the simple binary code. We looked at what is called as the BCD code or the binary coded decimal. We looked at something called the gray code. We also looked at what is the XS3 code. Now, one thing to note is that while these codes which we discussed, they have their own special features and whatnot. But the important thing is that these codes can be used to represent only numbers. So they are called as numeric codes. These are the codes which we had studied. However, the information that we deal with in day-to-day life is not numbers alone. It may have characters also. For example, A, B, C, D. You want to encode these characters also, then you need certain codes for that. For example, when you are typing on a keyboard, you don't always type numbers. You type alphabetical characters also. So therefore, there should be codes in binary for those sort of data also. So above and beyond numeric codes, we also deal with something that is called as alphanumeric codes. Which can encode both alphabetical characters as well as numerals like the numeric codes. So one of the first and most popular form of alphanumeric codes is something called as the ASCII code. This stands for American Standard Code for Information Interchange. So essentially, this is a 7-bit binary code. So where whatever is the numeral, the number or the alphabetical character, they are encoded as a 7-bit binary code. So the only difference is that unlike many of the numeric codes, it is not very easy to do arithmetic using numerals in ASCII, because over there every number is also treated like a character. Something you may know from your first course in programming. Let us say in C language, there is something called as a int for integers and a char for characters. You can add integers, you can subtract them, but it's very difficult to add or subtract character type variables. And ASCII is essentially just that. So over there, 7-bit binary codes are there not just for the numbers, but also for the characters. So over there, ASCII assigns characters for all the alphabetical letters from capital A to capital Z, then small a to small z, the numerals from 0 to 9, and also special characters. What do I mean when I say special characters? Things like space. When you type the space bar, the hash symbol, the dollar symbol, so on and so forth. They have codes for this also. So essentially, what happens is that using the 7-bit binary code, you can have a total of 2 raised to 7 possible combinations. That means you can represent up to 128 characters. So when you are talking about A to Z, first what is done is a decimal number is assigned to each of these. So from capital A to capital Z, you have 65 to 90 as the range of codes. After that, each of this is converted into binary. So what is the binary for 665? This is 65. So as you can see, this is a 7-bit code. What about capital Z? So this is for A, this is for Z. For uppercase Z, it is 90. And the binary code for that is 101 1010. For small a to small z, the range of decimal numbers is 97 to 122. Where 97 is for small a and 122 is for small z. So for 97, the binary code would be what? And for 122, the code is so the interesting thing to note is that for both capital A and small a, the last 4 digits start with 0001. And for uppercase or lowercase z, they end at 1010. So that is why the numberings are made this way. Now for 0 to 9, they are also assigned 7-bit binary codes. And that is from 48 to 57. So I leave it to you as an exercise to find out what the codes are. Now for these special characters, the decimal code is 32. So therefore, the binary code will be 0, 1, 0, 0, 0, 0, 0. For hash, it is 35. So therefore, it will be 0, 1, 0, 0, 0, 1, 1. And so on and so forth. So a character is assigned for each of these. Or rather, a code is assigned for each character. So you can have up to 128 characters, including the alphabetical, uppercase, lowercase, single digit numerals, and special characters. So many a time when you are writing a piece of code and you are dealing with characters, in underlying operations, it is the ASCII code of those characters which get invoked. So therefore, ASCII is a very, very well-known code. Let us look at the second kind of alphanumeric code which is there. So the second kind of alphanumeric code is what is called as a abecedic code. see over here, the word BCD is over here. And BCD, as we know, is binary coded decimal. So this code is based as an extension of the BCD code. So the full form of this is extended binary coded decimal interchange code, EBCD. This is an 8-bit code. Unlike the ASCII, which was a 7-bit code, EBCD is an 8-bit code. So what is done is, that the codes for each character, whether it is a alphabetical letter, whether it is a number, they are segregated in sort of groups of 9. Why 9? Because of BCD. They are grouped in groups of 9 and then assigned codes, and those groups are called as zones. So each group is called as a zone. Okay. So let us say, for example, I have the uppercase letters. A to I. There are 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 letters over here. So this will form one zone. Then let us say from J, K, L, M, N, O, P, Q, R. This will form another zone because there are 9 letters. So over here, let us say a code is given to each zone. So the zone code is, for this first zone, is 1100. This does not change for this group. And the code is a BCD code. So this is taken as 1. Of course, in pure BCD, even 0 is part of that BCD. But then that would make it 10 digits. Here, the 0 is not used. I'm sorry, this is 0, 1, 0, 0. This will be 0, 1, 0, 1. This will be 0, 1, 1, 0, 0, 1, 1, 1. Now for these groups, the zone is 1, 1, 0, 1. And this continues all the way till R. Once again, the numbering will start from 1 and all the way till 1001. So suppose somebody asks you, suppose I want to represent my initials. If I want to represent my initials in EBCD code, my initials are D and G. So for DG, the EBCD code would be first for D. So the 8-bit code for D is 1100 and for G it is 1100 So effectively the first 8 bits are for D and the last 8 bits are for G. This is how you represent DG or my initials in ABCD code. So therefore these kind of zones and codes are made for lowercase letters also and numbers also, and so on and so forth. So this is how ABCD actually works. Let us look at another kind of code. Although strictly speaking it is not binary, although the principles of that code is based on binary, and that is called as a Hollerith code. So Hollerith code is a optomechanical code. It is an optomechanical code. In this day and age, it is not very popular, but in the 1980s, 1990s and maybe till the early 2000s, they were quite popular. Why were they popular? If you interact, if you talk with any person who used to be a part of any company or who was a working professional during the 1980s or 90s or the early 2000s, in this day and age, when you go to work in a company, you may need to mark your attendance by giving a biometric input. You may need to press your thumb against a scanner and then it will read your biometric data and will mark you present. However, in the early days when biometrics reading was still very scarce, Hollerith code was the one which was used. So every employee in a company would be given a card which was very similar to an identity card. However, along with the identity card, there used to exist one more card. So that card would look something like this. This was a kind of metallic sheet which would have a series of circles. And so on. Now, these circles, some of them would be opaque and some of them would be transparent. So let us say if it is opaque, it would be like this, and transparent means it would be like this. So let us say the code in the first row is 0100 and the last 4 digits are 1101. So therefore this is 01001101. Second row, let us say it is 1010 and 1001. So this first row code is 01001101 and second row code is 10101001. So let us say one row corresponds to your name, one row corresponds to your employee number, just as an example. So they would have to, each employee would have to use this card, and there was a very special name for this card. This was called as a punch card. A punch card. So they would have to insert this card in a machine. So when at the start of the day, let us say morning 9 or 9:30, when employees would enter the office, they would have to line up in front of that machine and enter this card in that machine. And the machine has a series of photo generators and detectors where light would be passed through each and every hole. So obviously some holes where it is a 1, light would pass, and where it is opaque or a 0, the light would not pass. So accordingly, the reader on the other side would read a 0 or a 1. So this Hollerith code was encoded into punch cards and used as a optomechanical system for attendance or some kind of a reading. And this punch card would be the property of the company that was issued to every employee. But the problem is, obviously it would, if it gets lost, then it's a problem. Anybody else can impersonate you by using this card. Therefore, biometrics is better. But all said and done, in its day, the Hollerith code, which was encoded in the punch card, was quite a popular code which was used extensively. So that's all there is about alphanumeric codes. So of course there are many more. In the present day, there are codes which are more advanced for alphanumeric purposes, where you can use not only the known alphabetical characters, but also you can include a large number of special characters. For example, the pound symbol, the rupee symbol, more and more. So that is called as a Unicode. The Unicode discussion is extremely complex and is, strictly speaking, not a part of this course. But eventually, if any of you are interested, you can read more about it. Unicode is one of the most latest alphanumeric codes that are actually available, and it is used extensively. Having discussed thus far, let us now look at the electrical equivalent of these codes. Let us look at the electrical equivalent of the codes. The question we should now ask ourselves is that whether we have a simple binary code, whether we have a BCD code, whether we have a ASCII code, or whatever the code it is. Now the question is, in the electrical form, how do we represent them as signals? Well, we know, we have discussed that a 1 corresponds to a high voltage source and a 0 corresponds to a low voltage source. So suppose I have to express this code. I have to express this code in electrical form. What will I need? I will need a 5 volt source. I will need 0 volts. This is again 5 volts. This is 0 volts. This is 5 volts. 0 volts, 0 volts, and 5 volts. This is an 8-bit code. So ideally, I will need 8 5-volt sources because it can be all ones also. So that's like saying keeping multiple DC sources side by side. Now, one of the drawbacks is that the number of sources we need. So over here, what happens is that it is very wasteful in terms of resources. So therefore, even if we have multiple number of bits, we don't like to represent them electrically that way often. So, and the matter gets worse when the number of bits increases. So the question is now, how do we get around that fact that in spite of the fact that there are 8 bits and we may need 8 5-volt sources also. So therefore, representing these bits all at the same time is often not used. So what we do, rather than representing them all at the same time, we represent them one at a time. So we transmit 1 bit at a time. So you can transmit the LSB first, you can transmit the MSB first. It is up to you. So one of the easiest ways to represent is to send the MSB first or the LSB first, followed by the rest of the bits. That is called as a serial transmission. one bit after another. Now suppose I have the data, 8-bit data, or let us say 9 bits, or whatever it is. Let's 1 0 1 0 1 1 0 1. Let us say 8 bits of data I am transmitting. So one way I can transmit is in the form of pulses as a function of time. So this is as a function of time, the x-axis. So I am doing a serial transmission where one bit after the other I am sending. So first this bit comes, then this bit, then this bit, this bit, this bit, this bit, this bit. So now I can represent a 1 as a high level pulse. So let us say I am giving some time for each bit. So now 1 is 5 volts, 0 is 0 volts. Then again 1 is 5 volts. Then again 0 is 0 volts. Then we have 1 again. This is 5 volts. Once again we have a 1 which will be 5 volts. Then a 0 which is 0 volts. And finally a 1. This is 0 volts. So essentially it looks like a pulsating waveform. This kind of representation is called as unipolar. Because we have only 5 volt and 0. There are no negative voltages. However, from the electrical point of view, it is often useful to represent them in a bipolar form or a differential form. It's called unipolar logic, differential logic, where the 0 is not a 0 volts, but it is a minus 5 volts. So again, if you want to represent them, we will drop these lines over here. So 1 will be 5 volts, but 0 will be minus 5. So again, we will have 1, then minus 5, then plus 5 for 2 consecutive time durations, then minus 5, and once again at the end we will have a plus 5. So the differential logic is often used because it has better noise immunity. It has better noise immunity. Similarly, there can exist another form also. So this bipolar differential logic, as you can see, it is only oscillating between 5 and minus 5. There is no 0 over here. So therefore, this code is also called as bipolar non-return to 0 or NRZ, which means non-return to 0. Means there is no concept of non-return to 0. 0 is not used over here. However, another form of this bipolar is called as RZ or return to 0. Let us see what that means. So bipolar RZ. So for 5 initially this goes high for half this time. Then for the remaining half of this period it comes down to 0. This is plus 5. Then you have a 0 which is starting. So therefore this goes to minus 5 for half the time. And for the remaining half it comes back to 0. Then again for 1 it goes to plus 5 for half this time period, and then it comes down to 0. Likewise, this goes to -5 again and comes back to 0. Then again high for half the time, comes back to 0. Again high for half the time, comes back to 0. Then low for half the time, comes back to 0. High for half the time, comes back to 0. This is called as bipolar return to 0. So essentially, whatever is the way these signals are encoded, it is known to the transmitter and the receiver what is the form of these signals. So therefore, anybody who is looking on will probably not be sure about what kind of signaling it is. Although here they look very different, so you can probably make it out, but that's not always the case. There are many different kinds of representation. One of the other kinds of bipolar representation is what is called as a Manchester coding. That is also bipolar, but this is something little different in the sense that 1 and 0s are represented by transitions, not by levels. So the transition happens in the middle of this bit period. So each of this time is called as a bit period. Just like the RZ transition happens at the start of the bit period and also the middle of the bit period, the transition for Manchester coding happens at the middle of the bit period. So a 1 is indicated by a low to high transition, and the 0 is indicated by a high to low transition. So in the middle of the bit period, you have this low to high. This indicates a 1. A 0 means a high to low in the middle of the bit period. 1 means low to high. Again, 0 means high to low. Again, you have 1, that is low to high. Then again this comes down because it's a 1, and the low to high happens in the middle of the bit period. Then you have a 0, which is a high to low transition, and then you have a 1, which is a low to high. So the bit period starts at these dotted points, but the transition happens at the half of the bit period. So therefore, even this Manchester coding is quite useful. It is bipolar, +5 and -5. So in this particular lecture, we discussed about alphanumeric codes. We looked at the ASCII code, the EBCD code, and very briefly we discussed about the Hollerith code. Thereafter, we saw how the binary codes can be represented in a serial fashion, that is one after the other, because representing multiple bits at a time can be problematic because we may need that many sources. So rather than representing them side by side, we can represent them one after the other as a function of time. So therefore, these signals in serial form of representation are different. You can have unipolar form of logic, you can have bipolar or differential. Now, even in bipolar, there are many types: NRZ, RZ, and Manchester coding. So even the Manchester coding is actually a kind of NRZ form. So we shall continue from this point onwards in the next lecture. Thank you.